Okay, hello and welcome back to this tutorial on finding out the Fourier transform of the signum function. So in this video we are going to look at four ways of finding the Fourier transform of signum of t, and how does this signum of t look like in the graph. So this is the time axis, x-axis is the time axis, and for the positive time axis the value of signum of t is +1, and for the negative time the value is -1. This is t equal to 0 origin, and this you can denote as x of t as signum of t. So this is how the signum function looks like. Basically it's a sine function. Sine means sign, like whether it is plus or minus. So actually the problem with the signum of t is that it is a discontinuous signal, and therefore it does not satisfy the Dirichlet conditions, and therefore we cannot directly evaluate its Fourier transform using the formula. So we have to use some special methods for that. So, and here we are going to see four such methods. So first method is using the relation of signum of t with the u of t. So you know what is u of t. U of t is this unit step signal which looks like this. Till 0 nothing is happening, and at 0 suddenly the amplitude becomes 1, and the amplitude is constantly staying at 1 till infinite time. So that is the u of t definition. Now the relation of the signum of t with the u of t is something like this. Signum of t is given as 2 into u of t minus 1. So now you just believe that this formula is correct, and later I will show you the proof for that, because if I show the proof now it will interfere with the calculation. So just believe that this is correct, and then apply Fourier transform on both sides. And this 2 also you can write it outside, 2 into f of u of t minus f of 1. So here at the bottom there is some hint for us that u of t's Fourier transform is something like this: pi into del of omega plus 1 by j omega and minus f of 1. So what is the Fourier transform of 1? Actually, if you remember, del of t has a Fourier transform of 1 in the frequency domain, and as per the duality property, one will have a frequency domain, or one will have a Fourier transform of del of f, and since we are dealing with the omega notation, so for us it will be 2 pi into del of omega. So the same thing you write here, f of 1 is actually 2 pi into del of omega, right? 2 pi into del of omega, and you are left out with 2 by j omega, and therefore you can write the formula here. So Fourier transform of the signum function is equal to 2 by j omega. This is one method. So similarly we will see another few methods. So the second method is to use the relation with u of t and u of minus t. So actually the signum function is also defined as u of t minus u of minus of t, and for reference I have written our signum function here at the left side. So the graph of the signum function is like this, and the Fourier transform of the signum function we already evaluated. Just for reference I have kept it here, and now you just proceed with this formula. So second method is to use the relation of the signum of t with u of t and u of minus t. So therefore relation is like this: signum of t is equal to u of t minus u of minus t. So you have to believe this relation, and then do the same thing, apply Fourier transform on both sides. The operator should be linear. Okay, so suppose addition is linear, then subtraction is linear, like that. Derivation is a linear operation, integration is a linear operation, like that. Fourier is also a linear operation, so you are able to split it like this. But suppose if you have a log or exponential, you cannot split it easily like this. Okay, it is non-linear operator. Okay, so whereas Fourier transform is a linear operator, it will satisfy the linearity property. Therefore you are confidently able to split this as separately Fourier transform of u of t and separately Fourier transform of u of minus t. Okay, so far so good, but here we want to know what is the Fourier transform of u of t. So as in the previous slide, we can write it as pi into del of omega plus 1 by j omega. Then what is the Fourier transform of u of minus t. So here we have a small hint here. As per the time reversal property of the Fourier transform, if small x of t and capital X of omega are Fourier transform pairs, then the time reversed version x of minus t will have a Fourier transform of capital X of minus omega also. So wherever you see omega, replace with minus omega. See, del of omega is what? Just an arrow mark at omega equal to 0. So if you put minus omega, really nothing will change, because del function, if you remember, it's just an arrow mark here at omega equal to 0. This is omega axis, this is del of omega. So even if I substitute minus omega, nothing is going to change really. Okay, then this minus into inside minus. Okay, so this minus and this minus, so become plus, and 1 by j omega. So first pi into del of omega, this pi into del of omega, both are cancelled, so you are left out with 2 by j omega, which is your dream answer. Okay, desired answer. Then we will see what is the next method. Third method is actually to use u of t and the differentiation property. Okay, so again consider signum of t is equal to 2 into u of t minus 1 as in the first method. Okay, then what we are doing, the hint is also given, differentiating on both sides. Okay, d by dt of u of t. So if you remember, it is called as del of t. So your unit step function, if you take derivative, you will get the unit impulse. And d by dt of 1 is a constant, so d by dt is 0. So this second term is becoming 0. Okay, so you are left out with only this one, d by dt of signum of t is equal to this one. Now what you do, apply Fourier transform on both sides. Assume Fourier transform of signum of t is equal to some y. Then f of d by dt of signum of t will be equal to j omega y. Now this comparing j omega y equal to 2, right? Therefore you can write y is equal to 2 by j omega. Okay, what is y? In fact, actually it is the Fourier transform of the signum of t. So therefore again you are coming back to the same place where you started. Fourier transform of the signum function is equal to 2 by j omega. Okay, so just some mathematical trick, you have to imagine certain things and then you will get it very easily. Okay, so then we come to the last method. Consider the indirect method. So what is this indirect method? Actually we are relying on a signal x of t is equal to this one, exponential signal, where a is positive. So if a is positive, actually the signal looks something like this. On the positive time axis, it's dictated by this e power minus at u of t, which is a decaying exponential because a value is more than 0. Okay, this e power at u of minus t dictates the negative time. What you can do, take the Fourier transform of x of t. So therefore x of omega is equal to, as per the linearity property, you can take it as two separate Fourier transforms. Fourier transform of this is equal to 1 upon a plus j omega, and this is 1 upon a minus j omega. Now compare this on the left side. If you draw the signum function, so in the x of t, if a is equal to 0, then what happens? This becomes just u of t, and second term becomes minus u of minus t, and therefore it's equal to the signum function, right? So implies e power 0 t. Okay, so e power minus 0 into u of t, then e power 0 t into u of minus t. So if you put a equal to 0 there, you are getting u of t minus u of minus t, so which is actually a signum function, right? So once a value is becoming 0, this graph will become like this. Okay, and therefore in the time domain, if you take a is equal to 0, you are getting the signum function. So similarly, you take 0 in the frequency domain also. Wherever you see a, just replace with 0. So this is 1 by j omega plus 1 by j omega, that is 2 by j omega, which is our dream answer. So basically what we are trying to do is, first we evaluated the Fourier transform of this function. Okay, and then we are saying that in this function, if you put a is equal to 0, it will represent the signum function like this, because it's becoming u of t minus u of minus t, which we know it is a signum function. And therefore already you have the Fourier transform of that function. So in that you substitute a is equal to 0. Wherever you see a, you substitute 0, then you get this answer. So I think we have completed all the 4 methods. Now very quickly we will try to prove our these two things which we have just assumed earlier, so that our video will be complete in all respects. So first one, we have to prove signum of t is equal to 2 into u of t minus 1, which is somewhat simple compared to the second one. So u of t you know, then 2 into u of t also you know, its amplitude scaling, then 2 u of t minus 1. Okay, so from the 2 into u of t, you are subtracting 1, which is actually looking like signum of t, right? So first one is proved, second one we will see. So first we will draw u of t, then u of minus t. So u of t minus of u of minus t. Okay, so here you can also draw what is minus of u of minus t. So actually it is minus 1, because u of minus t is plus 1. Here you are putting overall minus, so it's minus 1. Amplitude of the signal is minus 1 throughout the negative time axis. So this is minus u of t. So this u of t minus u of minus t can be written as u of t plus of u of minus 2. So you're adding these two signals. So how does it look like when you add it? And that's all. So if you see this u of t minus u of minus t, it's exactly looking like our signum function, hence proved. So so hence proved is a famous statement in mathematics. If you don't know anything, just write 4-5 lines and then say that hence proved LHS is equal to RHS. Right. Okay, so I think we have nicely covered all the aspects of this video. Okay, so I hope that this video will be useful for you. So happy learning. Have a nice day. Take care. God bless you.